we're going to spend a little bit of time exploring roots and radicals. We saw a square root in a previous example. And a square root is simply defined to be that number, like the square root of a is a number which, when we square it, we get a. If we just think of it in those terms, we're left lacking a little bit, just because if you take this example here, 3 squared is 9, but if I square negative 3, that's also 9. So that begs the question, is the square root of 9 3, or is it negative 3, right? Both, when I think about the square root being just the number which when squared gives us what's inside, both 3 and negative 3 satisfy that definition. And we can't have a square root that means 2 different things. We would say that it was not well defined. So what we're going to do is just define the principal square root, and that is what we mean when we write the square root of a. It's the positive root. The principal root of the first root is the positive root. This symbol here is called the radical. When there's no number written in it, it's understood to be a square root. Otherwise, we can look at other roots like cube roots or fourth roots or fifth roots, and in that case, they would put a little number inside. So, like this means cube root. And if there's nothing written, it's understood to be the square root. So it's understood that there'd be, like, say, an implied 2 inside the crook of that radical sign. So now, knowing that this is the principal square root, we know that the square root of 9 is 3, not negative 3. And if we wanted to refer to that negative root, we would just put a negative outside. So the cube root of a number is the number which, when cubed, gives us a. And just in general, the principal nth root is a number which, when raised to the nth power, yields a. So this, you could sort of think of this equation right here as a really succinct definition of what a radical is, the nth root of a number. If I raise that to the nth power, it gives us the number inside. We're going to evaluate some roots. So in the beginning, these first few are ones that we could do, we'd say, by inspection. They're going to be kind of convenient numbers that we're working with. So the cube root of 27, we'll just note that the cube root of 27 is 3, and this is because 3 cubed, which is 3 times 3 times 3, is 27. The square root of 0.04, so we have a decimal here, but still, this is going to be, you know, knowing that these are convenient numbers, I'm going to think of maybe a more clever way to write this. This is the square root of 4 over 100, right, 4 100ths. And this is 2 tenths. And that's because 2 over 10 times 2 over 10 is equal to 4 over 100, right, which is 0.04. So if we wanted to use decimals here, we could say that the square root of 0.04 is 0.2. Our last one here on this page, the cube root of -8. Well, the cube root of -8 is -2, and this is because -2 cubed, -2 times -2 times -2, this is +4 times -2, and that gives us -8. We might be a little uncomfortable at first seeing a negative inside a radical. I think we're all very used to the fact that we can't have a square root of a negative. And that's true. The square root of a negative number is not a real number. It does not exist in the real numbers. But the cube root of negative numbers do exist. In fact, as long as it's an odd root, odd roots of negative numbers exist in the real numbers. We're going to do some work simplifying radicals. So if a radical expression is simplified, if we've removed all perfect, like, nth powers, like let's say I'm working with the nth root of an expression, I want to take out any nth powers. I don't want any radicals in the denominator of a fraction, and I prefer not to have fractions inside the radical. And now we can use these properties to help us simplify. The nth root of a product a times b, I can split up that radical over multiplication. I can also split up a radical over division, and that's what we see over here on the right side. And here's just a word of caution: we cannot split up a radical under addition or subtraction. If you see addition or subtraction happening inside a radical, just make yourself slow down and think carefully about your steps. It can be easy to make mistakes. All right, so we're going to spend some time simplifying. And one of the first things that this says up here is all nth powers have been removed. So this next example, we're working with the square root of 48. It's a square root, so I want to remove any perfect squared factors, is what that first kind of bullet item says. There's a couple of different ways we can think about this. I'll show you my favorite way that I think is pretty simple. Is I start by factoring. So making a factor tree, 48 is 4 times 12, and 12 is 4 times 3. Now I can go all the way down to primes if I want, but I'm stopping right here because I notice that I have a pair. This is a square root, so we usually don't write this in, but I'm going to just indicate that that's the index of that radical is 2. So I've got the square root of 4 times 3. And if you have a pair of the same factor inside a square root, then you can bring that out as a single factor. So that's 4 times the square root of 3. When we talk about removing perfect nth powers, or in this case, in this example, be removing perfect squares, I might have, if I want to think about it as removing perfect squares, I might have written that as 4 squared times 3. And if you have a perfect square, that comes out as a single factor. So either way, 4 times the square root of 3. And you can check. I'm going to just open up the calculator here real quick. You can, at least these numerical examples, you can check your work and see that you get the right answer. So on the one hand, I'm going to just put in the square root of 48. Right? That's going to give me some approximation, 6.928, blah, 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 blah. Now, next what I'll do is put in 4 times the square root of 3. That's what I got when I simplified, and if I did it right, these should give me precisely the same value back. 4 square root 3, and there it is, identical digit for digit. In our next example, we have the cube root of 40. So I'm paying special attention to the fact that this is a cube root, so that means I need 3 of the same factor in order to take one out, or in other words, I'm looking for a perfect cube. 40 is, 8 times 5, and 8 is 2 times 4, and 4 is 2 times 2. So we have the cube root of 2 times 2 times 2 times 5. So because it's a cube root, I'm looking for 3 of the same factor to be able to take one out, and there's a group of 3 2's. So I'm going to bring out a 2. Now all the 2's are gone from inside the radical. 2 times the cube root of 5. Again, you could check on the calculator, plugging in the cube root of 40. Now, depending on the model of calculator that you have, you can get to a cube root if you hit the math button on your TI-84, and you can see it's option 4 here. You could put in any root using option 5. It'll ask you what root you want to take. But I can do the cube root of 40, and that gives me 3 point something, right? And now next I'll do 2 times the cube root of 5, and we get the same thing. You can also, if you don't have this menu that allows you to bring up a cube root or any other root, just note that, and we'll spend some more time on this in the future, but a radical is the same as a fraction exponent. So for example, the square root of x is the same as x to the 1/2 power. The cube root of x is the same as x to the 1/3 power, and so on. So just real quick here, I'll take 40 and I'll raise it to the 1/3 power, and that gives me the same result as when I took the cube root of 40. Okay, In our next example, 1 over the square root of 3. So right now we're not in a position where we have perfect squares to take out, but we do have a square root in the bottom. That's something that we want to fix. So here's what we do. We take this process, we call it rationalizing the denominator. So the problem right now as it exists is that I have a square root of 3 in the bottom, and the way I'm going to fix it is I'm going to multiply. I'm allowed to multiply the top and the bottom of a fraction by the same thing, and I'm going to multiply by the square root of 3. On top, 1 times the square root of 3 is the square root of 3. On the bottom, the square root of 3 times the square root of 3 is 3. That's the definition of the square root of 3, is that if I multiply it by itself, I get 3. So this is our final result. There can be no reducing here. 3, I cannot cancel the 3's because one's in a radical and one is not in a radical. So they're off limits for canceling, and that's as far as we can go. In this next one, I have a fraction inside the radical. That is generally just as unappealing as having a radical in the denominator. So what I'm going to do first here is, now this isn't always an option, but I notice that 3 actually goes into 25. So I'm going to reduce. 3 goes into 75, rather, 25 times. So this is 1 over 25. And now I'm going to split up this radical over division. So I got root 1 over root 25. And in fact, 1 and 25 are both perfect squares. It's just 1 over 5. So I didn't need to employ that trick where we multiply by a radical. This kind of simplified really nicely without having to do that. I simply had to use the fact that I could split up a radical over division. Now, if I hadn't noticed in the beginning that 3 goes into 75, that's okay. I could still do this problem. I would just start by splitting up the fraction. I would note that 75 is 3 times 25, and 25 is 5 times 5. I'd say, okay, there's a pair of 5s, so I can take one out. And then, at this point, I'd probably say, look, I've got a common factor of the square root of 3 on the top and the bottom, and I can cancel. And we still get 1/5. So all roads lead to the same correct answer. All right, and our next example, I'm going to slow myself right down here because I have addition happening inside the radical. So these properties about looking for squares, looking for the same factor, so I could take out a factor. All of those things assume that I am looking at what's inside the radical in a factored form. So no addition, right? Just multiplication. So the first thing I actually need to do here is figure out, well, what is this value inside the radical? 6 squared is 36, and 36 plus 18 is 54. So I have the square root of 54. Now that I have done that part, now I can think about factoring and taking out square factors. So 54, let's make a factor tree. 54 is 2 times 27. 27 is 3 times 9, and 9 is 3 times 3. So this is the square root of 2 times 3 times 3 times 3. I've got a pair of 3's I can take out. This gives us 3 times the square root of, and left inside, 2 times 3 is 6. And there's our result. Now I can check again, because it's a numerical example, I can throw this in a calculator and check. So if I have, let's see, the square root of, inside it was 6 squared plus 18, gives us that result. And now 3 times the square root of 6 gives us exactly the same thing. Okay. In our last example, we have, it's not purely numerical anymore. I've got some variables, but everything is multiplication. That's good. And it's a cube root, so I'm just taking note of that because I need 3 of the same factor to bring one out, or in other words, I'm looking for perfect cubes. I'm going to factor 24. 24 is 3 times 8, and 8 is 2 cubed. So I've got 2 cubed times 3, and there's the 24. X to the 4th, I'm actually going to choose to write that as x cubed times x, and then times y cubed. Now, I could have written x to the 4th as x squared times x squared. It's more helpful to write it as x cubed times y cubed because, oh, and I forgot to write it, the index of this radical is 3. I need perfect cubes. So I'm going to take out an x, I'm going to take out a y, I'm going to take out a 2. So outside of this radical, I've got 2xy. So once I do that, then those are gone. And what's left inside is 3x. So 2xy times the cube root of 3x.